Welcome everyone to March. Good to have you all here. So, quick show of hands before we get into our normal questions. Who here is here for the first time? Okay, how did you hear about it? Meetup. Okay. I don't remember Meetup. Twitter. All right. Blue Sky, anyone? No? All right, we're on there.
Friend of mine.
Friend of yours?
From
From
George.
George. Well, George is the kingpin here. Yes. Yes, he's the linchpin. All right. So, first up, what we always do, who is hiring? Last month we had 2 people hiring. Who's hiring this month? Where's Andy? Andy's usually hiring. All right, but Andy's not here. All right. What's his name from last month? John Sherman. I think he's still hiring for his health food startup. So check out last month's video, and you'll see I think he's still hiring, and maybe Andy is. That's how we're going to do it. Check out last month's video to see who's hiring. Hopefully they still are. All right, we have fallen to hard economic times. But that's not my problem right now today. Got to get through this. So, since no one's hiring, let's drown our sorrows in this pizza. So, everyone is here in the room. Yep, you all, my regulars know what to do. Pull out your phone. Go to bit.ly/pizza poll, and we have a 5-point scale. Tell us how the pizza is. For those of you that are new, we've been tracking this data for about 12 to 13 years now. Every month we have pizza from different places. Sometimes we do some repeats, so it's sort of longitudinal. And we have the live data feeds available at jaredlander.com/data, and you can get a live feed in JSON of the voting as it comes in. And if you go to nyhackr.org and click on more, you'll see a live graph of it.
Where did you order it from?
Oh, yes, today is from Marinara. All right, so the very top is from Marinara, so go in there and rank that on our 5-point scale. All right, we've been collecting this data for years, so it's very important we keep this going. Those of you joining us virtually, let us know what you're eating. If you're eating pizza in some other place, not here, we'll still consider it pizza if it's not from Chicago. New Haven's cool. Paul, I got you. Detroit's awesome, but let us know what you're eating. If it's not pizza, let us know. Just be a part of the conversation. Speaking of being a part of the conversation, if you want to join the conversation and you are virtual, you want to ask a question of our speaker, just want to comment on stuff like what you're eating, where you're coming from, you have 2 chances to do that. You can either do it right in the YouTube comments, and we do check that, or you could do it in our Slack. We have the nyhackr Slack. If you need an invitation, you go to nyhackr.org and click on the Slack button. And if you post your questions or comments in the monthly Meetup chat channel, then we will collate them and we will ask those questions of our speaker toward the end of the talk. So join our Slack or ask us in YouTube. Same goes if you're hiring, go to our Slack, again, nyhackr.org, find Slack, and go to the job postings channel and post your job in there if you can't be here in person to offer people jobs. And also at nyhackr.org, you'll be able to find all of our past talks. We have about 15 years of slides and about 10 to 12 years worth of video, depending if those services have been shut down. We had a whole bunch of videos at livestream.com, and they just got rid of them all at one point. So that's why we do our own videos now on YouTube, and we keep track of it all. So nyhackr.org, which is written in R, so you can go find that and go find some of our previous talks. We have the next few months planned out. In April, we have Garo right here. He'll be speaking. So look forward to that. The announcement will be made very soon. And then in May, we have Paul, not this Paul, different, you almost freaked out there. A different Paul will be speaking. He's not here, but Paul will be speaking in May. That'll be announced after the April meetup. We do not have June or July or August confirmed yet. So if anyone wants to give a talk, come find me, come find Nicole, come find Carla, let us know, and we'll arrange for a speaking slot. If no one volunteers, I will offer people. That's how Garo got this. I just told him he was speaking, and he was cool with it. So I will have to voluntold people at some point if we don't get enough volunteers for this, okay? So please let us know if you'd like to speak. A big round of applause for George, who every month makes this happen. Thank you very much, George. And George is here under his auspices of the NYU Prism Center, who has been graciously hosting us for well over a year now, and have been a really good partner of us to make this thing work out and give us this beautiful space overlooking the park, usually heated. So we are very happy to be here. But thank you. And again, while it is NYU Prism, George is our linchpin making this happen. So thank you very much, George. Yeah. After the talk, we're going to go to one of George's favorite bars.
Don't quote me on that.
We're going to repeat at Malt House. So Malt House has been pretty good to us the past few times. Malt House is on Thompson, above Bleecker, I want to say, between Bleecker and Houston.
Just in front of Bleecker.
Just in front of Bleecker. I told you it's his favorite place. Again, if you don't drink alcohol, come. They have mocktails. They have food. If you don't want that because it's too much sugar, just come and hang out and have a nice conversation. It's just a really fun way to extend the meetup and just enjoy each other's company for a little bit longer. So if you don't want to drink, just come and hang out and have fun. All right? So with that, I think that is all the announcements we have to make. We have April and May planned, but we need future speakers. If you're going to post a job, you're going to do it in job postings. My virtual folks, you are going to ask questions in the monthly meetup chat channel or on YouTube. And everyone ranked at the pizza. So I think we have everything covered. So I'd like to welcome two-time speaker. This time, and I'm hoping there's going to be some Jeff Goldblum references here, talking about chaos and machine learning. Everyone please welcome Vikram again.
I was thinking of avoiding it. Welcome, everybody. Apropos to the title, we had a little bit of trouble starting this whole thing with the HDMI cable and so on. But now we're good, all set. This is roughly the outline I want to follow through, which is start off with a few examples of what, or at least one example that explains what chaos is. What are some of the characteristics and definition? And if we have the time to, we'll look at predicting in chaotic systems and impact on differential learning. Essentially, the second part of it is going to talk about where and how we look at chaos and its interaction with deep learning systems or machine learning systems. The thrust of this talk would be on recognizing and understanding what chaos is and what it is not. And then finally, we'll open it up to Q&A. All right, before we get started, I threw in a bunch of words in there. So some of them are physical systems, some of them are mathematical models. I want to see what folks think of as being chaotic or not. So planetary motion, for example. You think it is chaotic. Okay. Cardiac rhythm. Okay. What about random number generation? All right, what about matrix factorization? All right. I'll come back to this in a little bit. I wanted to see where people, people think of, just to get a taste of the audience. Through an example, right? Chaos through an example. A good starting point for us to build a mental model of chaos is through looking at the various categories of dynamical systems. It's invariably a condition or a state within dynamical systems. There are 4 categories. If you want to be pedantic about it: continuous, discrete, stochastic, and symbolic. What is easy for us to work with is a discrete system, an iterated system. So we'll focus on that, and then we'll build up an intuition based on an example. Let's start with something rather simple, right? How many of you have heard of the logistic map? All right, great. This is great. I'm assuming biologist? No? All right. All right. This was made popularized or made famous by Robert May in 1970s, if I'm not mistaken. It's simply this rather simple-looking formulation where xn plus 1 is a quadratic expression of xn, right? And then there are some contingencies or conditions within which we want to inspect this this formulation. And of course, you can think this is an iterated system. You start with x1, compute x2, then you plug in x2, and then compute x3, and so on, right? Just simple quadratic equation. But one of the reasons that I throw it out there is it is one-dimensional. It allows us to build an intuition. Right? The second thing is, if you look closely here, x is a placeholder for a state. So if you have a dynamical system, an iterated dynamical system, x is a placeholder for state, r is a placeholder for a parameter, right? Very simple. It allows us to build some sort of an intuition about it. So now if we plot this, right, we get something like this. Way on the left, I've now marked up r being 2.7. I've thrown that number out there so that it's visible and it's called out, right? What do I have here? By the way, does anyone know what's a cobweb plot? All right, great. Essentially, I'm starting off with x1 equal 0.1 or so. You draw a line all the way up to the curve. That is your x2 value. You mark it off on the left-hand side. I think it's like 0.2 or so. Then you draw a horizontal line onto the 45-degree line. That allows you to project up from that spot over to the next point on the curve, and so on. So if you did that iteratively, where you would end up eventually and converge to would be that point close to 0.6 or so, 0.6, 0.7 maybe. And this is a cobweb plot. This is famously used, so you can actually visualize and demonstrate convergence. This scenario or this condition or this situation would be called a fixed point condition, right? We have a dynamical system where the iterated dynamical system where the input variable changes over time, or the value that we spit out at every point in time changes, but interestingly we have a convergence point here. So if we made that a little bit interesting to see, this is what you would get, right? Just going through the motions of it. All right, after having entertained ourselves with that, let's take a look at this. So all I did was changed the value of r, the parameter, right? By the way, the parameter r, as it increases, you would get sharper and steeper curves, higher up and so on. But when you have r equal 3.45, what you would find, and if you run it sufficiently long, is that it doesn't converge to that intersecting point that we thought it would converge to. What you would find is there are level sets, if you want to call them level sets, at which it converges, or at which you would find on the left hand, on the y-axis, a darker red dot, because that point gets visited over and over, or that vicinity gets visited over and over, right? So you would see, I haven't marked it off, but you would see those the horizontal lines getting darker and darker. There are 4 of them that are getting darker. This one would call a periodic orbit or a periodic window within which there is a period of 4. There are 4 different values that you're approaching. Now, if I changed it to the r value to 3.6, you get something like this. And certainly there is no convergence here. There is no period x number I can associate this to. This is a blot over 2 different regions. In fact, it may be 3 different regions, perhaps with a bit of a disconnected regions, 2 of them in there on the y-axis. Of course, mathematicians are interested, and the next thing they jump off to say, hey, let's study the relationship between r and these terminal values of these xn's. And this is a famous diagram. It's called a bifurcation diagram. You look at r on the x-axis and the quote-unquote terminal value of the x's as you go through the iterated system, right? Well before 3.0, you have this one point that it converges on, which is the fixed point. And then somewhere around 3, you find 2 points that you converge on, or rather jump back and forth between. That's a period 2 window, meaning if you look at the vertical red line between the first vertical red line and the second vertical red line, you see 2 distinct values that the xn's would eventually jump around between. And if you look farther out, you see another period doubling happening. You see 4 different values that it settles at. And this is corresponding roughly to the plot that I showed you for 3.45, right? Those are periodic orbits. And then rather immediately, quickly, you find another set of vertical red lines, and you see a period of period 8. And it would appear to us that the pace at which these period doubling happens accelerates. If you look at the window, right, the first window is larger, the second one is narrower, and so on. So of course there has been study of that done as well. And this phenomenon is called period doubling. And the people have studied the ratio between the window sizes and that ratio happens to be called Feigenbaum constant. It has some universality properties, not just applies to this logistic map function, it also applies to several other functions with similar characteristics. But rather quickly, you would attain infinite period doubling. And that point is called the accumulation point, and it happens to be somewhere around 3.6. It's 3.569 or so. And I've marked out there in a little box, tiny box at the bottom, that says the onset of chaos. So this simple looking quadratic formulation, quadratic function, has a region where you find specific discrete periodic doubling and periods between which the values, terminal values, jump and oscillate. But then after a certain point in time, I don't know whether it comes through clearly on the slides, there is a gray region that you see. The values jump around not with distinct level sets, but across regions almost randomly. Right? This is the onset of chaos, this region, right? And that would have been satisfactory to most of us, and we would have said, okay, that's great. We have this behavior. There's there is what appears to be chaotic, what appears to be disorderly behavior in that region. But if I zoom in to that region past the accumulation point, you would find this. This should be disturbing to most of us in the sense that the expectation would be after the 3.6 value, everything would be a dark region, but that's not what happens. You would find a period 3 window, a period 5 window, and so on and so forth, interspersed in the mix of that, the chaotic region. And that is a characteristic of chaos. In the sense, of course, you are in the chaotic region, but interspersed in the chaotic region, you could find periodic windows where there is some stability between periodic orbits. All right, let's move on to the, what I've also done further is I think I've expanded on the window between 3.6 and 3.7 and said, all right, what do we see? Well, the same thing. You expand it, you find similar things. So this may make folks think of some sort of a similar structure, self-similar structure at different scales, right? You expand into deeper and deeper scales, you find self-similar structure. Some of the observations that would lead us to defining or crystallizing the definition of chaos would be this: period doubling accelerates, at least in this one-dimensional case. Chaos reigns after the accumulation point. And the strange thing is the chaotic region contains periodic windows of all periods embedded with it. And of course, I briefly mentioned about Feigenbaum constant. There are some universality conditions, universality properties about it, which applies to single quadratic maps, one hump graphs. Even cubic functions also within certain regions exhibit this property. And this is just a previous slide that I showed. What I want you to focus here is this right here I'm showing is within the region of chaos. 3.9 is the value of the parameter R. What I've done is I've started off with 2 distinct starting point values. And I'm following them along to see how they diverge or how they behave over time. And in this case, time is not what I'm using just steps, right? So you would find that the red and the blue completely overlap for the first almost 18 or so time steps. Somewhere around the 18th time step, they just start diverging. Okay. Now remember, the difference between them is 1,000th, 0.001. And just to highlight the fact that the difference the difference diverges rather quickly, I've plotted on the bottom in green in log scale the difference, right? So we start off with 10 to the power of -3, and you would see that it's 3 orders of magnitude higher when it comes down to like after 20 iterations or so. This is a characteristic of chaos. If you look at it very closely, one might see that if there was any correlation between the two values, x1 and x2, the red and the blue here, initially, rather quickly, you would enter into uncorrelated region. All sorts of predictability are lost. This divergence, of course, has been studied well, and folks have, this is just a static map of that, have constructed what is known as a Lyapunov exponent that allows us to study what is the rate of divergence of two starting points that are very close. This is defined for this definition, as I show here, is for a continuous function. You can also have a discrete correspondence to this. And then you can plot the Lyapunov exponent and see what the behaviors are. One thing that might be obvious for folks who are inclined to mathematical or symbolic manipulation is that this exponent, if it's negative, is the region of convergence, which means you get periodic windows, you get fixed points, and so on. But when the exponent is greater than 0, you have this chaotic region, right? So if you look at that 0 line and anything over it is the chaotic region. Anything to the left of that is, but remember, even within chaotic region, you will see this frequent dipping down into non-chaotic periodic windows. All right, here's so we've spoken and shown, looked at an example of how a 1D map behaves, kind of have a notion of what chaotic region is, but we're going to crystallize that with the definition a little bit in a slide or two. But this is a brief history of things. Unfortunately or fortunately, the only thing that most of us happen to recognize is the 1963 row right there, which is the butterfly effect by Lawrence and Jared's reference to Goldblum, right? It was in Jurassic Park, right? Yeah. Unfortunately, that's all we are left with, but that's perhaps a good starting point as well. This last work is quite important for mathematicians, right? If you see a period 3 window, it actually implies chaos and so on. A few takeaways from the properties that I've shown you would be nonlinearity, although I might not have emphasized it, a boundedness, so that if the function actually goes off into the wild, it may not be interesting. And then attractors. I haven't defined or stated what exactly an attractor is, but if you have a periodic window that it jumps around between, you might call them attractors. A single point would be a fixed point. When it is otherwise between windows, between values, then you call them attractors. And when you are in the chaotic region, you call them strange attractors. Yeah, the aperiodic is called strange attractors, and that's that. Here is something I got off the web just to entertain myself. This is based off of Lorentz system, which is a toy system now. It's for fluid convection, or just before fluid goes into a convectional motion between 2 plates and so on. But what's important to notice here is that there is never a crossover of this plot on a previous line. So it never really ever gets to the same state space that it previously has. And of course, it's possible to look through that. Another thing that is important is that within the region around the 2 attractors, and you may call them attractors, the curve actually is quite densely packed. So if you study analysis, there is the notion of packing something densely, and that's what it does. And let me see how I got that. Right. These are the non-linear equations that form the foundation of that the plot that I showed you. All right. Now, finally, this is the definition, right? There are a few key words key phrases to recognize so that we really understand what chaos is. Sensitivity to initial conditions, a periodicity which is along the lines of never crossing over the graph ever, right? You never visit the same state. And then the third phrase in a deterministic unpredictability, all it is saying is that we have a deterministic function. The function xn plus 1 equal x1 multiplied by 1 minus x1 is a deterministic function. There's nothing unpredictable about it. But the deterministic unpredictability is because depending on how the resolution and the scale at which your input variables are defined, your output values after 100 motions, 100 iterations could be quite unpredictable. And additionally, what makes it interesting is the whole thing happens in a bounded state space. If I were to give you a nonlinear function like e to the power of x, it's not interesting anymore. We know we would have diverging values, but we're not really interested. No, this is what makes it interesting. All right, now let's get back to this, the stuff that you threw out there and some of the. So anything in green that I have there is non-chaotic in the sense that, so matrix factorization is not chaotic. It's a mathematical game that we play. Linear regression, we apply it in real world. It's it's a linear. There is nothing non-linear about it. A random number generator, of course, is not chaotic, although chaotic regimes of systems of functions like these can be used to create what are known as pseudo-random number generator, pseudo-random numbers, which behave like random numbers, but they are not truly random numbers. Randomness requires stochasticity, and you require rolling of a die, right? So this is, chaotic systems are not like that. They have to be deterministic functions, and they exhibit this chaotic behavior in a particular regime of the parameters. Everything that is not highlighted is chaotic, but again I have to be very careful here what we mean by that. Meaning that not that these physical systems are chaotic, we do not really know how these physical systems are, but the closest mathematical models that we build to approximate these physical systems have regimes within which they operate chaotically. That's a mouthful, but I think it's important to recognize that we truly do not know how weather patterns behave. We have models that emulate that, but most of the models use certain mathematical expressions and mathematical systems. Those systems are chaotic, and they have regimes in which they could behave chaotically. All right. Now that was the first part of the talk, and perhaps the emphasis of the talk. The next portion I'm going to quickly go over two distinct ways in which chaos has been looked at. One is, can we use machine learning to predict chaotic systems, how they behave over a particular a particular number of steps, over a specific horizon. That's one. The second one is, how does chaos impact machine learning, specifically differential programming or differential learning. So this comes to us, again, this is just a sampling of things that one could look at in terms of machine learning and chaos. Here, this work comes from the world of reservoir computing, and the folks in this who apply these techniques would like to predict in the short range, for example, weather as an example. And there is a network known as echo state network that is used to predict something like one time step ahead weather as an example, right? Or maybe even a week ahead or so. What exactly is the echo state network? Well, it's a bunch of neurons they call it a reservoir in the middle of the network, and there's a layer in the beginning, that's the UN, and there's a layer at the end. There are some teacher signals or supervised signals, and there's an error that you can compute, typically mean squared errors, because these are regression targets. And then the dotted lines show us the learning that truly happens. The only learning truly happens at the output layer. The rest of the layers are frozen solid. They are randomly chosen high dimensional vectors, vector spaces in which you are computing these recurrent steps. One might think this is quite arbitrary, but interestingly, this happens to work very well for certain domains. What do we have? We have a layer that takes the input, transports it to the higher dimension, and then several of that, and then finally down to the prediction layer. You may look at it closely and say there is a hidden vector that is computed. F is a nonlinear function, and then you have an output that is predicted. All the learning is essentially in the W out. The W out can be learned using linear regression, like regularized regression. Here I'm showing ridge regression, and out you read. So you send a batch of data, meaning a time series of data. You get a bunch of errors. You do not have to compute any gradient or anything. You just simply directly compute W out, and that's your learned model. Remember, all the layers within the reservoir are frozen solid. This offers the benefit that there is no back propagation through time. That's what BPTT stands for there. Rapid learning and inference. The guarantees for this model are, of course, through universal function approximator from the world of recurrent neural nets and so on. And apparently, this kind of modeling has been successful in the world of weather and climate modeling, wireless communication signal processing, and so on. I do not know whether this is actively used in other domains, but these are the domains that it has been applied in. And what is to be noted that it is quite a daunting task to be able to predict in the regime of chaotic systems. And they, in these domains, have been able to claim that they can predict up to 5 times the Lyapunov exponent, which is actually quite admirable. The final portion of the talk, just quickly going to talk about chaos and how it impacts differential programming, which is standard deep neural nets, artificial network, and so on, artificial neural nets, and so on. Again, the key here being some sort of iterated dynamics happens, and we want to learn through that. You can look at any autoregressive model as an example, a recurrent neural net as an example. This is the general formulation of what happens. There is a state at time t, it gets transformed into state at time t plus 1. There's a nonlinear function parameterized by theta. The loss, of course, you can write it out. I know these slides may not be that appealing or interesting, but mathematical expressions. But eventually, at some point, if you actually have to learn, you have to push differentiation through that, and you have to compute the gradient, and you could get a formulation like this. I've only written out 2 of these lines. If you do the very general expression, you get something like this. And what would be immediately an alarm bell going off for folks who are inclined to looking at symbolic expressions like these would be the multiplication I from k to t for the partial differential of Si over Si minus 1, which is the Jacobian of the function f with respect to the states. Right? So you have the series of multiplications that apply, and very quickly you would find that the behavior of the entire gradient, the gradient with the loss, is dominated by this, or not so, depending on the eigenspectrum of the Jacobian matrix. Right? Meaning this is, and very quickly that will lead us immediately to say, oh, we have a exploding gradient or a vanishing gradient problem. Right? Only to say that we're further reinforcing the fact that this is a real problem, and even more so in the case of chaotic systems, because very close by starting points can actually diverge, and you can have very different gradients. Just to get a summarized understanding of all that symbolic manipulation that I showed you is this, right? Chaos can break differential programming, and the spectrum of the Jacobians determines the stability of your gradient that you learn. And the final point is an empirical thing that we can observe. I'm going to quickly show a slide that shows this. There are 2 networks. One has been initialized with the orange dots. One has been shown in orange dots, the other one in blue dots. The one in blue dots is initialized randomly without any tuning or control of it. The one in orange dots have been multiplied down by a certain factor so that they fall within the unit ball, right? And what one would see then very quickly is that if you look at the product of the Jacobians, which is the plot C, It is dimensionally 7 times higher. The order of magnitude is like 7 times what you would find with the orange plot. And of course, you can see when you get a gradient of that size, each step that you take may actually throw you off the learning path completely. And finally, the gradient of the norms, the norm of the gradient, sorry, is also an order of 3 orders of magnitude higher. Only to further restate that chaos could actually wreak chaos into your machine learning systems, into your learning programs. There are some mitigations here. There are common techniques of gradient clipping, truncated gradient propagation, etc. I'll leave you guys with a few references to go in and look at. Before I go to the Q&A, there's one thing I want you guys to walk away with from this entire show would be this plot, right? How you diverge rather quickly, and then maybe this plot where you actually have a bifurcation diagram and periods of chaotic regime with periodic windows in it. Those are the only 2 takeaways. If those were the only 2 takeaways you had from this talk, then I'll be happy. With that, I'll open it up to questions, please. Please.
The reservoir computing thing always blows my mind a little bit. And so I have a question about what type of dynamical system you're allowed for the reservoir. So if you're using it for weather prediction, where you actually know what the equations are, could you just put Navier-Stokes on the Earth as your reservoir and then learn the outputs? Is there some rule for what types of systems, what type of neural networks give you a good reservoir?
I see. So the question is, do we have any studies on what type of networks would give us a good reservoir for a particular domain?
Yeah. I guess maybe my question is related to, on one slide when you talked about chaos prediction, you showed ergodic properties question mark, and maybe you didn't talk about it.
Yeah.
And you could argue that probably just a random reservoir is not going to preserve constraints on the weather system, just because that would be very and so you could imagine that there'd be some advantage to simulating it using the laws of physics. Yeah, I'm sorry if it's a vague question. I was just curious if you could just throw if you can use any system as a reservoir, could you use the actual system somehow do better?
So the question is, if we could throw any system as the reservoir, could you actually use a dynamical system, an evaluation system? Yeah, it could, but yeah, it could. I mean, it could mean one could, I guess, but I want to state a few things there. One is the use of echo state networks.
Is that essential? Sorry, is that essential for the? I'll let you finish.
Yeah, the use of echo state systems, in my understanding, has been in ensembles. So it's never really that you have thrown this. So the networks are created randomly. Here, go back here. Yeah. The interconnection between the networks, the weights of the network, all the layers except the last layer are randomly chosen. And let's assume it's a univariate case, right? Single variate with a single scalar number. The essential foundation of what makes it learnable in this scenario is the fact that you're projecting that single scalar into a very large dimension. So specifically, from the papers that people have worked on in this field, you would see that they would take a scalar and they would project it to 1,000 dimensions, almost 1,000 times more. So by the universal function approximator principle or theorem, the idea is that if you take any variable into a much larger dimension, it is quite possible that you've separated them into independent components that allows you to learn. Now, you wouldn't a responsible way to use this system, a setup like this would not be have one echo state network. You would have multiple of them, an ensemble of them, and the predictions from them would give you a distribution over what is possible, right? And that is what has been done, in my understanding. Now, coming to your question about physics and applying physics, there are physics-informed neural nets, and they have been around for a while now. I think at least 5 to 10 years, if I'm not mistaken, in which the formulation is quite different. The formulation is not of a neuron that learns or runs a particular mathematical expression, but what you do is you construct a neural net, and the loss function is where you apply the physics that you know, the dynamics that you know.
So you'll have like an energy conservation.
Exactly. So something along those lines is applied in the loss, so that enforces on the loss the physics of your system. Does that?
Yeah, that makes a lot of sense.
Yeah. So that's it. By the way, that is also a work that is actively happening in this domain as well. Okay. Yeah. Please.
Yeah, the way some dynamical systems have closed form solutions, could you unravel this echo state network into like a feed-forward network? That way, things won't be exposed as poorly.
So let me try to get the question.
Like some dynamical systems, you could just solve for a closed form solution.
Right.
You don't have to iterate. I was wondering if you could do something here with like the gradients and sort of invert it to get, like, can we use a feed-forward network instead? That way we don't have all these dependencies.
So can we use a feed-forward network? Perhaps you could, but remember, the task here is to essentially attempt to predict what a chaotic system is trying to do. And a chaotic system only occurs if you have nonlinear interactions. And possibly it is the case that you are having nonlinear repeated iterated interactions. And if that is not happening, perhaps, you know, this, but you have a valid point. Can we apply the single feed-forward neural network technique with this echo state kind of architecture? Possibly you could. I have no. But all that you are doing there essentially then becomes that you have one learning layer in a feed-forward network. Does that help? Okay. Please.
So if you have a prediction task, can you use the Lyapunov exponents to like decide if it's worth throwing a alert or not? They give you some kind of bounds on how effective ML will be in that scenario.
So just to repeat the question, if you have a learning task and if we were able to compute the Lyapunov exponent, can we use that as a guidance to see if it's worth putting together a machine learning model to actually learn? Am I getting it right?
Yeah.
Okay. So the short answer is I do not know. Where I have seen Lyapunov exponent being used is in comparing the performance of your model to what is expected of your prediction, right? How good is your model is where you would use the Lyapunov exponent. If you're able to compute the Lyapunov exponent, in some cases it's not easy, it's not a converging that expression, Lyapunov exponent, may not be computable, right? But in most cases, if you can compute the Lyapunov exponent, where it has been used is to see how good is your machine learning model under various regimes of input data, to see how many times Lyapunov exponent how many multiples of the Lyapunov exponent is your prediction still a valid prediction? So specifically in the use of echo state networks and for the weather modeling in the toy data sets that I have seen, is that people have claimed up to 5 times Lyapunov exponent, which is quite good, which means you can almost think of it as 2 to the power 5, like 32 times what would be possible otherwise, right? It's more like benchmarks as opposed to working it backwards to see whether it's even worthwhile building a machine learning model or a system. But you have a very valid question. Can the exponent itself tell me anything about the effort that we're undertaking? Yeah, I do not have an educated response for that.
You're not virtual, so not too many questions as usual.
That's right.
Does he go further?
I can keep asking questions if you have that.
Please do. Yeah.
So something like, if I was studying a chaotic system, that I would love to be able to do would be to find the unstable invariant structures. Is there any chance that this trained echo state network could be used to do that on a time series? I don't know. You can say you have no idea. It's fine.
Yeah, I don't know. I just want to get the question right.
Yeah. So you have you showed the Lorentz attractor, right?
Right.
And so the Lorentz attractor is filled with unstable equilibria and unstable periodic solutions, and those are kind of those could be used to build perhaps a statistical mechanics of the trajectories on the attractor, because solutions tend to come in and stay close to the invariant structures for a long time, because they have some stable manifold. And so I'm sorry, I'm just curious if this could be helpful for that.
I see.
Could,
Right. Yeah, I see what you mean. Okay. Is it possible to tease out the ergodic properties of these attractors using echo state networks?
Would an echo state network predict the periodic orbit? Could it if you ran it a bunch of times, if you just kept running this time series out, let's say you use because you can just keep running this over and over again, right? Would the dynamics of that be chaotic? Or would it converge? Do you know if that's known?
Yeah, good question. There is work in using echo state networks to actually quantify the ergodic properties of the attractors. That means the regions where you repeatedly visit but not really converge, quote unquote, but densely pack around, echo state networks have been used to study those properties. What you mentioned, which is running it repeatedly, which is what we call autonomous mode of operation for these. You feed the output back into the input and then you run repeatedly. After 5 or so times, 5 multiples of the Lyapunov exponent, your predictions wouldn't be any good.
True, but might you still be on the attractor?
Possibly on the attractor, yes. But I do not think there are guarantees of that. But you're right, that has been used to study the ergodic properties of the attractors. Maybe quantitative descriptions that allow us to say, but again, there may be quite a bit of uncertainty in those predictions as well. Some variance in what is being predicted about the properties of those attractors. Yeah. I mean, I hope it captures the essence of your question.
Yeah.
Okay.
So big round of applause. I have to be the immature one and say, where are the dinosaurs? The whole talk, I set you up for this, and no dinosaurs. All right, so if anyone has any further questions, Vikram's coming to the bar, right? So you come to the bar and have a chat with him. So remember, April, we have Garo speaking about graphs.
Graphs, linear algebra, applications of them. It won't be too theoretical.
Not theoretical graphs and linear algebra. I'm not even sure how you're going to do that. It's going to be awesome. All right. Remember, if you are hiring, please go ahead and post that at the job postings channel. And I guess that is all. Thank you again to George and NYU for hosting us here. And remember, we're going to Malt House. We're just going to take a little bit of time to break down. Oh, there's still 1.5 pizzas left. 1 box or 2. Our pizza algorithm broke down this month, so we need everyone to go have a slice before you leave. Can we lock the doors as we usually do before we leave? All right, everyone needs to have this. We don't want to have any pizza left behind. All right, so remember, Malt House, come back in April for Garo, come back in May for Paul. We'll have other announcements coming up later, and post any jobs you have in the job postings channel. And with that, one more round of applause for Vikram. And thank you all for being here. Thank you for tuning in virtually, and we'll see you next month. Bye, folks.